Maybe one question right now is like we are in the era of the big models. So there's the frontier models that very few labs have access, and they are very powerful. And then we have like the world of maybe the startups and academia, where we are limited to a few GPU. And the question is like, how can we cross the gap between the open source community, which is like the startups and the academia, and go as close as possible from the frontier model? So I know that DeepSeek and Llama are doing this, but through the similar method of centralized training, relatively the same kind of methods as the big labs are using. The question is like all those topics that we saw during that workshop, could they enable us to close that gap, or are we doomed to have forever gap in between?
I think it's a good question. I think probably the answer is if we want to have a competitor to all of these big labs in an open or decentralized setting, it needs to make sense economically. All of the money that go into training these models are not negligible, talking billions of dollars to build data center. And I think either collaboration via university cluster, public funded, or a bit more sustainable, decentralized organization is probably the only way to have something so you can do competition with what the big labs can do in terms of money.
I will agree with what Sami said, but I will also say that the advances, like the algorithmic advances in centralized training, are somewhat underrated for even open source model development. So if you see, like there was a paper, I believe last year, about algorithmic improvements in deep learning scaling, which shows that definitely a lot of the advantages like come strictly with like putting more compute into training, but there is a lot of improvements in efficiency, like in getting better and higher quality models, even at low scales, even with relatively smaller compute, by using smarter algorithms, by approaching the way we train on data in like better than just like taking whatever data we have. So I think by combining those two directions, like having a way to develop models collaboratively, but also not forgetting that we can improve the core training loop itself, I think that's going to be the most impactful way to advance for the open communities and for the academia.
I would even take it to more extreme, what the previous speaker says. And when you first asked this question, I thought, why? Why would academia want to train these crazy large language models? What's the goal? So there are different theories. How do we get to the AGI or best model possible? It's scaling theory. We need to train bigger. It's data theory. We need to train on more data, multimodal. Or it's architecture theory. Nobody knows the answer, but I like to believe it's architecture, and that's the open question for academia. You don't need to train on billions parameters to explore new architectures.
That's a follow-up question on that. There's also the idea of like democratizing, access to these models and being able to train. So that's also like an axis along which like you want to think about how the role that academia has. But in terms of the discussion, we've basically been talking about distributed training, distributed algorithms. But what is the role of data? We've talked about the role of architecture, but what is the role of data when it comes to thinking about distributed training and distributed algorithms? Should we be treating the data differently? Should we be doing more interesting things with the way we distribute the data?
I think for pre-training, at least the data doesn't like the data is scrubbed for internet basically and collected and used for pre-training. So I don't think that there is a big improvement to do at the data level in the slow resources and academic level. I think that distribution and decentralized start to make more sense data-wise in a reinforcement learning setting. I think reinforcement learning is a way to actively sample and actively source data. So you have a model which is not only trained in a black box, but kind of interacting with multiple sources. And I think in this setting, distribution actually starts to make sense. Actually have a competitive advantage. Like if you have a model which is distributed everywhere, you actually have a richer environment, richer information of data that could eventually lead to better model. So yeah, I would say reinforcement learning is different than pre-training to this regard.
Yeah, I actually have a slightly different perspective on this. And to me, there is definitely a potential to benefit, even in terms of data volume, to a certain degree, from decentralization. So, to my understanding, you can imagine some companies or organizations which have access to like private data that they don't want to share with anyone, like especially with companies which develop like closed frontier models because they don't know what's going to happen to this data. But if we found a way for them to like somehow contribute to training models on that data without that data actually leaving their premises, there is a chance that we'll be able to like produce better models, especially for the applications that those organizations care about, by like leveraging those places where the data is stored. Obviously, yeah, like there are some setups where you cannot just send data to someone else.
Maybe tying this to, I think, the first question on motivating how companies can release more models. I think if academia demonstrates that designing a model that can be where continual learning and continuous updating the model is kind of the right way to do this, then this gives a strong incentive for a design of such an architecture. And there specifically data is quite interesting because you would not be able to train on all the data available all the time. There's different data sources that are available during pre-training. They get updated frequently, and in order for the community to actually help keep the model updated, but being able to adapt to proprietary data and so on very efficiently, developing these algorithms is quite interesting. Maybe also kind of looking back at a time where releasing these models was very interesting. Well, where basically academia could leverage a lot of these times. So I think that's demonstrating that this is very interesting. Is a good direction to look at.
I still don't feel like the question of data quality, data cleaning, like deduping, decontamination is really being addressed here. Like that's a very difficult coordination problem, and it takes immense resources to train frontier models. With those, with that work being very, very crucial to reaching frontier levels. So how do you feel like the decentralized community can tackle that? I don't feel like just throwing as much data as possible at the problem is sufficient, but feel free to disagree with that as well.
Yeah, actually, that's a really good point. I was thinking about saying something in that line, but I was also not sure it was context of here or not, because I think it would be modular, but it's not context of algorithmic modularity, but in the context of, I don't know, maybe I'm general open science or like a modular research, let's say, let's phrase in that way. But actually, there are good examples. We had this, I mean, on not we, but we also had, there are lots of open science projects that people come together and collect data, right? Because data collection is really center of many things. And how we design the algorithms to like combine central and decentralized approaches together. Actually, data collection also same way. And actually, I'm not sharing the negativity in the same way, because it depends on what kind of data you are collecting. Maybe the people that are contributing the data might be the experts for like how clean that data are, right? I think in that sense, definitely there's long way, open way to go collecting data from communities or people, in my opinion. I'm not connecting this with the decentralized training, because I think you collect data, centralize it, then again decentralize it, probably. Yeah.
Sorry, deduplication is quite important as well. Like if you have too many duplications of data.
Yeah, definitely. That doesn't address that one.
Okay.
Yeah. Well, to answer your question, I guess that to a certain degree, a lot of problems and like computational challenges in data preprocessing could be like they are to a certain degree embarrassingly parallel. So unless you consider deduplication specifically, where you do need to consider things like the hashes or like the duplicates can remain on different nodes or like on different participants. The rest, I think, is very like susceptible or like very easily adaptable to the standard MapReduce paradigm, more or less. So I would say that this is probably even more easily scalable than standard, than decentralized training of large models, because your requirement to communicate is lower. Like you only have to communicate the end results apart from the step where you do dedupe. So I think, yeah, and here you also can use way fewer resources unless you do something GPU heavy. So yeah, in my opinion, it's even more scalable, at least for those steps. That again, I'm not an expert in data processing, so maybe there are some steps which would be harder.
I guess like yeah, I do agree that data quality research itself is super important. That is like some fraction of the research I do other than modular learning. I do think like reducing the expense of like deciding like, oh, like how should you be mixing your data? Is this data even useful? Doing that in a way that's like actually computationally viable, like I believe that's a really open area of research and like also super exciting. I think, oh man, I saw like 5 different data mixture some papers on open review like for this conference. So I think I agree that it's important, but I think just like making that cheaper is something that's totally possible to do.
Yeah, I think it's interesting also because you can think about how like you can use these decentralized compute that we have to actually make those data decisions, right? Maybe you can do some interesting things locally that you can then like, uplift to basically like on the global scale. I wanted to ask a question around, I wanted to ask a question around, we've talked about a little bit about like elastic compute and basically kind of like changing the model size depending on kind of like the resource needs. I haven't seen any work that kind of synergizes the idea of elastic compute and distributed training, but it seems like a kind of like seems like a natural place to be thinking about elastic compute, right? Because you have a lot of different kind of nodes over which you can train. Some of them drop out. The notion of dropping nodes basically corresponds to the notion of like having different subsets of the model. So why is there not like, at least in my opinion, why is there not that much work in looking at how elastic compute plays with decentralized training?
All right. So yeah, that's a very interesting question actually, and to me, one of the reasons why there is not a lot of research in the space is that a lot of variation in the volume of compute that you have is not a very common setup. Like even in volunteer computing, you can usually expect that like there is some stable value around which you fluctuate. So there can definitely be some approaches like, I think even like with the DMOE paper, which I've mentioned in my talk, so sorry about advertising, it's possible to like scale to additional experts. But in principle, a lot of like approaches which try to dynamically adjust the model capability are specifically like almost directly designed to benefit from this. So the more compute that you have, like the more you can scale horizontally. And the question is like, which models can be very easily cut or like again extended when you need to, or like when you have more resources. So yeah, that's at least my perspective.
Yeah, I'm not from the distributed training community, but it just seems quite intuitive to also integrate different versions of the model, like early exit or things like that, into the training pipeline, so that maybe not all nodes are supposed to have the same objective, but share parameters or something. Smaller nodes have smaller model versions. So something like system 1, system 2 kind of processing to just adapt to the compute resources that are available on the respective nodes. Yeah.
Maybe to continue on that, like elastic compute, what about like not doing training, but the inference? So like reasoning model are so costly, so slow. How can we maybe through like speculative decoding, but also maybe Matformer or other kind of method? Can we have a constellation of model and how to route properly?
I was about to comment on the same thing as inference, but from a slightly different perspective. So you can have like speculative decoding, you can have accelerated inference with more compute, but also maybe like if you have more resources, you could have like for RL, for example, more like longer reasoning steps or like just longer trajectories to train. So like ultimately that benefits your model training because it sees more data, it sees more like difficult data and so on. But it's like, again, like not about the architecture or the model itself. You just scale inference. And as we can see, like from papers like OpenAI even and others, it scales a lot with just like more compute put into it.
I agree with what you're saying. I think one of the reasons why it's difficult to design elastic architecture and co-design elasticity in distributed training is because I think we fundamentally don't really understand how neural networks are working, and it's difficult to engineer around this, and so we end up with having this like architectures that are relatively rigid, and we barely know how to train them, and so it's difficult to like engineering, for example, an early exit and things like this. I think it's fundamentally because we don't understand how the dynamic are working. One thing that we understand a bit more is how inference is working and how to dynamically allocate compute at inference time. I think this test time scaling paradigm of training is actually the most elastic compute things that we can do right now.
I guess I'll also kind of answer the question before I get back to this part of the question. I think like one thing about like thinking about like, oh, we're doing this decentralized computing and we want to have different types of essentially different programs running on different nodes and different devices. That is actually kind of hard to do. And also when you do, so there are two things you could do. You could decide, okay, we might want to train an elastic compute algorithm that's either training from scratch, or you might want to do something that's post hoc. So that could be something like test time scaling. That could be something like, oh, fine tuning with Matformer. I think there's a bunch of people at NVIDIA who did that and got some really good results. I think the reason that happens is that it's like honestly way easier to get predictable results. I've had some experiments with, so I think generally like the more heterogeneity you're adding to your pre-training algorithm, which is like super long, super expensive, you want to be able to predict how this is going to behave. And that's like actually really hard to do.
Maybe like to jump up of this, like it's hard to make some algorithm that is more heterogeneous and predict it correctly. So you work on like on architecture, modular architecture. Also, like the topic of this workshop is like collaborative. All the algorithms that we have mentioned in terms of modularity or the architecture are always not really collaborative, or at least step by step. I train my module, then you train your module, but never all together. So if it's going to be even more heterogeneous, even more complicated, so can we then predict how it will behave in that kind of setting, more collaborative?
I actually don't think I understood.
Sorry, it's maybe not clear. It's like the question is like, the more heterogeneous the architecture it is, the more maybe harder it will be to predict, which is dangerous when you want to scale. But if you want to go really collaborative, where we all train our model together, so in the case of adapters, we all train the LoRa in parallel together. In case of Matformer, we each have a different subset of the parameter, or in BTX, a different subset that then is regularly merged as an MOE. In that case, can we do really collaborative training, where each of us bring their own maybe architecture, data, algorithm, and all together while being predictably behaving?
I think that's like something where you actually really need to think hard about like the compiler side of things. And I mean, okay, how are you going to compile your program when you have a very heterogeneous architecture? How do you want to rethink your kernels? Like I think some folks like made some changes to the MegaBlocks kernel and like had a talk at this workshop today. And I think like thinking from that, it's like, oh, can we do this with like our existing approaches, or do we need to make some changes before we do these types of collaborative things? So I think there's people here who have way more expertise on this part than me.
So it's an engineering problem?
Yes, I think it definitely goes super hand in hand.
regarding elasticity, I think, Jonas, you mentioned also that prompt engineering is also a way of, thinking about modularity. Not only thinking about LLMs, but also like models like decision transformer and so on in terms of reinforcement learning. Do you think that this could be something that changes the way we might transfer also like what codes how our model works, because we just exchange like relevant contexts, and could this be a more efficient way of also as a community exchanging relevant programming, so to say, of the model?
I think that's what people are already kind of doing, right? I think everybody gets kind of those tweets of like, you are only on level 1 of your ChatGPT experience. You should step up your game with these 5 prompts or something like that. So I think everybody has seen those. And to some degree, I guess that is collaboration in terms of exchanging modules. That is like, specific to the desires that you have of using that model.
Taking this a step further, thinking about like, could we develop architectures that are not made for language, but like sequence-based, as for example, decision transformer, where you basically get an agent out of it by defining a trajectory, like the future behavior is conditioned on the past trajectory, and then we just, maybe compress those trajectories and communicate that. Do you think this is a like more efficient way of exchanging like updates, for example, like do learning on top of that?
I think that's a very interesting research direction. Yeah.
On the question of modularity, it's actually not clear to me that we really want to merge all of the adaptator. I think we take it as a basis, but the point of adaptability is to have some specialization, and it's not clear that stacking all of the specialization together is necessary. I think the image diffusion community is a good example of how they really managed to nail adaptator based on, like, for example, stable diffusion model, where people have like some really small adaptators that do one use case and they don't need to stack them together. You can combine 2 of them together, but it's very plug and play. Maybe there is something similar in like the more large language model space that we could do.
Yeah, I kind of agree. I think getting back to, I guess, that initial question of if we have to do some kind of heterogeneous pre-training already, and it feels like that's overcomplicating from a pure future research direction. I think obviously that would be amazing, but from a more pragmatic perspective, I think the whole workshop here shows that all of those steps are already super difficult, and doing heterogeneous pre-training is something that is unimaginable, I think, at the current time, just because we don't really know how to do distributed pre-training efficiently, or like we haven't solved that issue yet. But maybe thinking of how to do heterogeneous post-training then, how to integrate the respective distributions that people are interested in, them designing heterogeneous architectures, and then designing the pre-training model to kind of cover all those heterogeneous things that might be relevant during post-training on the respective distributions, and effectively being able to just integrate them with existing algorithms is a step in the right direction to then have enough knowledge to actually maybe do everything at once.
So the hardware lottery of Saint-Rocher said that it's hard to beat the alternatives, as you're saying, because it's so well optimized. So distributed method, modular method, new optimizer, they don't work as well usually because you are facing like hundreds of years of optimization against you. So you will argue that basically a researcher should first try to beat that wall by going to the post-training, which would be maybe adapting existing models, which would be maybe easier cost in terms of time, compute, and effect, before going to the pre-training and starting from scratch.
No, what I meant more like is if you're trying to design, like pre-train on a mixture of data and have a different architecture for each portion of that mixture. That is, I don't know, for vision and language examples, you have a completely different architecture part than, or a specific subset of that, if it's like snapshots of code versus if it's images of cats, I don't know, and trying to integrate all of that very dynamically. It seems like, or code has different bigger modules and all of that, while distributing it across everything. Seems like, you have so many moving parts that you're trying to optimize for. Like, I truly believe that that's necessary. Like, you need to, different distributions need different amount of capacity. But figuring that out, that size, has so many moving parts. You have to find so many new scaling laws. That's just very difficult, just from the start.
Yeah, I wanted to add that maybe it was already done to some degree in multimodal model of the last couple of years, when we tried to do it combine different modalities in different ways, where we have maybe pre-trained large models, and then we kind of try to merge them together into one single big multimodal model. We have existing models that are doing that, and they were trained embarrassingly parallel. Maybe they're not working together as one big monolithic model. That's another thing, because they were trained completely independently. But then another approach, when you have this bunch of adapters that combine different modalities, different aspects into one big model, and then train it together. But then also that one big model doesn't have to be one monolithic. It can be a set of experts. And then why don't you have modality-specific experts? It can be not necessarily modalities. We were talking about multilingual models, and can be domain-specific experts, and so on and so on. So I think it's not done in the sense that we have all the answers, but there are some research in this direction that started over the last years, and it's going to be interesting to see if it goes anywhere.
When you ask collaborative training or something, but the term of collaboration, in my mind, first, like, why we also not think collaborative inference? Because this actually allow us to, think modularity not part of a one thing, like a one monolith something, but we can have like a multiple black boxes. We may not really also care about what are these, but we can actually, I think still there is, for example, inference time scaling is one way to do that. But even beyond, I don't want to say like agent, but we can have like multiple different things that people train. How can we use them in a collaborative manner efficiently? I think it's still open question. Like, we have multiple ideas about like simply routing inputs to trained models, but I feel like this is not really enough, because we need to have much more hierarchical collaboration between already trained models, and I think we are still lacking thinking modularity in that manner, in my opinion.
Yeah. So getting back to Artur's question, and also based on what Olga has proposed, I would say that there are two different approaches, like at least in my mind, about what to do if you have like different model architectures trained on different data sets, and it depends on how you want to use the final result. So if you need to have a singular model, there is that's an open research question. So maybe you can distill all of them into one model, but the question is, should you? So one approach which has already been proven to work to some degree for like LLMs in general is you have a kind of a router that dispatches your request, whatever you want to do with a model. Like, you have multiple models under the hood which are specialized. So it's kind of an expert, but built post hoc, based purely on the fact that you have those multiple like models for modalities or for different domains of data. So like that's the simplest solution we could have. Obviously, there is a lot of potential for additional research because like we could build them hierarchically. We could also like improve on it in other ways. But I think like the major dichotomy is like on what you decide to do with all of the models once you finish the training.
I wanted to add why not inference, merging on the inference time. Branch train merge is merging on the inference time. And the problem with this, it's not fine-tunable. That's why we had to go to further branch train mix. Because when everyone wants in the end fine-tune on your specific task, and you have bunch of models, and how do you fine-tune on your task this bunch of models? So.
Very quickly. Yeah, I totally agree. Like actually, I was also thinking in that way. But even beyond like a branch train mix style modeling, because still you are building a bunting, right? After you have experts, I think even beyond like having completely separate experts, routing them, or like routing or some way composing them in some way. I think that's way to go in my mind. Like I think we should really open this connection bound, maybe break it, and define the modularity or like collaborative. How do you say like collaborative inference in that manner? I think it's quite promising in my mind.
So it's two parts. The first part, I'm curious, what is the consensus among you? Maybe not now, maybe only in the future. Is it important that an expert or a LoRa is specifically good at something we as humans can comprehend? Or is it okay if an expert is just good at a bunch of stuff that we don't even know, as humans, we don't even know what links these things together? And if we think of experts in this way, I think I don't know. I'm wondering. So the second part is this helpful? Because then we can think of all of this as a way more of a common heterogeneous problem. That then maybe there's less of a proper separation between things, and maybe that helps for distributed learning, because everything is just a weighted, the weights we learn them, of course, a weighted mixture of experts, the same way we think of Gaussian processes with the Dirichlet distribution. Like, is there a way we can think about it this way?
It's a good question. I think it boils down to defining what is specialization in an expert. You ask a question about should the expert be like a human expert? I would argue that no. I think we should have as less structure as possible, so that we can have like nice algorithms that are going to emerge. I think mixture expert is actually a weird name because it's not clear that there is a clear specialization. It's more like a distribution. But I think the question of specialization and expert is very important in a collaborative and distributed setting. It's not clear right now that model needs specialization. It's like actually it's probably the other way around. Like the best model are kind of best at good at a lot of tasks at the same time, and everything moves at the same time. And I think asking the question of can we actually create specialization that is useful for moving capability is probably the most important question to know how all of these heterogeneous inference or training are going to evolve.
So basically, the question is, do we make the modules interpretable or not? And I think it depends on the scenario that you're interested in. Specifically for efficiency purposes, interpretable modules are desirable because we don't have to deploy them on all devices. Whereas if you just throw everything, you assuming you've come up with a system that that scales and you can have indefinite modules, then you don't care, right? It should select all of that dynamically. So I think there's a pragmatic answer that you should sparsely activate them, meaning that for sparse activation, you do need some sort of specialization because specifically if you train an MOE with load balancing loss, an example will activate all experts, full stop. If you don't want to deploy all those experts on a device, that becomes a problem because that's how you trained it. And so, I think that's a more pragmatic way of thinking this about this. If you know a specific expert has learned a specific distribution, like in this version of MOEs that you say do what you want, and then you do post specialization, you ideally want to identify some experts that have learned vision or something like that, because that's how you can adapt it to a new domain. So yeah, I think that's my answer.
To answer this question, I actually wanted to refer to a poster I saw in this conference, very interesting in my opinion. And so we usually enforce some expert specialization on the model, but it actually can occur naturally in the large pre-training. So they propose the model with some crazy number of experts, like 200 or something, that they pre-train from scratch, and to that experts all know these problems of unequal distribution, they propose to use actual two routing models and then recombine them together, and they show that it stabilizes training. But what else cool in my opinion that they show is that the experts actually specialize in domains naturally. And then they show distributions by task, and then they turn off some of the domain and they degrade on specific domains, but not on the others. So maybe that's something that occurs naturally, like order from house.
Yeah, so I will both agree and disagree with what everyone has said, right, everyone here. So like from the point of view of like having interpretable or non-interpretable experts, definitely if we approach it from just like the beta lesson point of view, then it's more beneficial to have like less enforced like inductive bias into the expert, because we'll learn everything like automatically. And one of the reasons why deep learning is actually like dominating a lot of fields right now is that we don't do manual feature engineering. So from that point of view, I would agree that, well, like if we were to view it strictly from that, I would say that this is the way to go. And also, just like was mentioned right now, there is a way for experts to specialize naturally, purely based on the fact that like if you have disparate domains of data in like this high dimensional space, then it's beneficial for the model to be able to specifically like point to that part of the data and to allocate a specific expert to use this. So like it's like from the learning perspective, it kind of makes sense. However, I wouldn't completely discount the interpretability aspect of it. So like even if we don't need to, like even if we can filter data out like by natural means, it's still important like and helpful sometimes to understand like which parts, or maybe like to identify which parts of a model, as in like in terms of modules, were tasked to learn a particular like domain in the data or a particular topic. This might be helpful for reasons of just like understanding which parts are learned better. This might be more helpful to understand the capacity that needs to be allocated to a particular domain. So again, well, I will agree that it depends on the final goal.
I still have the feeling that we are overusing the term expert here. I think mixture of expert, the expert is mixture of expert is not as specialized as we think we are, even though there are some kind of routing. I think actually specialization is a core feature of learning in general. I think we should rather approach it from this angle rather than from the routing angle, which I think is more a distribution of the computation rather than true specialization. I think what we want is probably self-improving models that can naturally specialize on some task. And in this setup, then it kind of makes sense to have a distribution of a million of experts, and each of them will hold real specialization on some task and maybe collaborate with each other. But I think that current setup of mixture of experts right now is kind of really far away from this ideal expert and specialization scenario.
Yeah, I don't disagree. I think, an MOE is a very big term. So if we think about MOEs right now, it's specifically a sparse MOE that does token level routing with load balancing activated. So then I agree, like it won't learn anything specialized because the load balancing loss enforces just sharding across devices. But an MOE is also, if you think about training adapters across the collaboration space, you are also training an MOE, where the router is the human that selects the respective expert. So, you know, there's a spectrum of MOEs. So that term is kind of very broad, and depending on how you train the respective experts, they do have to become specialized, and they can just learn a specific task. Yeah.
I wanted to take that idea to the extreme, actually. So yes, like the term mixture of experts, the term expert is overloaded a bit, but I would say that, like again, the specialization is a necessary feature of learning, and if you think about it, even individual neurons in a neural network, like even in a feed-forward layer, like on MNIST or whatever, they already like necessarily have to specialize in some way to like get specific features activated. So I would say that experts in the mixture of experts model, like regardless of the routing algorithm, are specialized in the same way that neurons, like in a feed-forward linear layer, are specialized, just in a more coarse-grained way. We do not always understand what that specialization is, and again, that's like a property and a benefit of deep learning benefit. But that doesn't make them specialize less. We just don't understand it.
Hi. So I have a rather general question. So we've been talking a lot about like decentralized training, decentralized inference. But my question is, do you think the current research in AI, in large language models, is going to be decentralized or centralized? Because we've been seeing like GPUs, monies are just flowing into big companies. And as like students staying in academia, we seems to be lacking a lot of resources. So what do you think of it?
I think that's one of the reasons why decentralized has not been that much developed in the last year. Is there were no strong incentive in making it happen. And it's something I was trying to explain during my talk. I think things are changing, both at the very large scale and at the frontier, and both at the academic level. And I think both will actually naturally evolve with something more distributed and decentralized, mainly from a cost perspective and from an ease of use perspective. I would argue at both levels we're going to evolve a more distributed setting.
So yeah, we've seen some signs in the industry, but not that many of them. Well, maybe enough, but not as many as some of us would like to see in the academia and like in the open communities. And I think I agree that this is mainly a question of tooling that's available and which is not scary to use, so to speak. So as long as people understand that those methods are like available to them and can be used to produce better models or just to experiment at a scale that was not previously available to academics or to independent researchers, then I think the field will start moving in that direction. Because again, like right now, everything is kind of like maybe not stuck, but like very used to this standard way of doing things. So the question is like how to move it to the other part of the spectrum.
I would like to ask a kind of connected question. I think other things that we do, including the decentralized training, including the modular approach, it depends partially on the technical side, the thing works, and partially on the like each individual making the decision that I'm going to contribute my data, my compute, my module artifact to the thing, and making the decision that I'm going to try this instead of GPT. And so also to make that decision, they also need to know the thing exists in the first place. So do you have thoughts to share on both like getting the thing known and having the incentives right that they will be accepted?
I can go maybe on this one. I mean, I think beyond machine learning, I think the world have seen multiple very successful collaboration happening at the individual level. Things like Wikipedia, things like internet have kind of naturally emerged of collaboration. I think the same could happen in AI. I think that the fact that AI is and a compute is so expensive make it that probably you need to carefully craft incentive and probably economically incentive and people to collaborate. But yeah, it's something that need to be engineered, the collaboration to make it work. It's a definitely non-trivial problem.
Yeah, I think one big difficulty is that during pre-training, you have to come up with a version of the architecture that is not going to hurt anything else in the mixture. And that makes it very difficult to do that. So depending on the domain that you're an expert in, you might want to make nuances of architecture changes, and that's that might hurt the performance on many other things. So here, I think, is a interesting direction where you can define these adaptations as an architecture change, and coming up with a routing decision doesn't have to be the router that we have in mind all the time, but some kind of automatic decision process that selects the respective architecture at the correct time, making it much more collaborative because individual teams can optimize integrate their domain knowledge of the data, but also the types of features that are processed. Very, very difficult to solve that, but I think that's kind of how the past research has looked like, that somebody focused on one specific task that they're like very interested in, that they're an expert in. And so they came up with kind of that novel LSTM architecture that was designed for that specific NLI task, for example. And then they published that. And now we've converged kind of on one specific architecture. So yeah, maybe one has to think about that direction again, but it's very, very difficult.
Thanks. So I learned a lot from all of you. I want to understand, where do you see us heading? Like, I don't want a very short-term view, but probably next 3 to 5 years, because a lot of compute is going to become abundant. HBMs are going to go up that are attached to GPUs, and the network between GPUs as well as between servers is going to become faster and faster. So there are a lot of things that are happening. For example, Muon optimizer, right? So Kimi published a paper that with Muon optimizer, they achieved the same low loss with half the number of tokens. That is half the number of flops, right? So there is probably a lot of money on the table that is still there. On the other end, people are cleaning up data. The way fee from Microsoft showed, you can achieve same MMLU with much lower data if it is curated properly. And last but not least, while MOE models are great, training them is hard. Like MOE models achieve high MMLU at much lower compute. That's great. But after that, running inference with them at equal efficiency at which, say, for example, DeepSeek is running is extremely hard. So NVIDIA is trying to introduce libraries like Dynamo and all that. So all those things are happening, but that is super, super complex. So do you think that in next 3 to 5 years, the compute will become so abundant that we will all forget distributed training and all these complexities of mixture of experts and simply be training only dense models with very nicely curated data and maybe better optimizers like Muon?
I think there is room for both, in the sense that we are probably going to train smaller models that can be deployed everywhere, but at the same time, if compute become cheaper and more abundant and interconnected become better, why not train bigger model? So I think both will happen at the same time. But I think that decentralization and heterogeneous compute will probably have a big impact in the ability of scaling model. Again, I think all of the big labs are thinking as well in this direction, is like how to continue scaling in the current paradigm, and obvious answer seems to be to go a little bit more distributed, a little bit more heterogeneous.
Yeah, I actually agree on that point that the more compute we have, like there is a tendency that the more compute you have, like you don't have idle compute, regardless of how many you have of it. So like if we are getting like more efficient chips, which are able to perform more operations and they are cheaper, then it will mean that we'll be able to run like maybe more like compute intensive operations even as part of standard deep learning or inference, which means that the capabilities that the models exhibit right now will probably be continue growing at least to a certain degree. So yeah, my point of view is that this trend, like we've seen the Moore's law, we've seen like other trends in increasing compute, and always the industry, regardless of like whatever that is, like computer graphics, whatever, it has kind of kept up its demand, so that the new every new generation of compute unlocks new opportunities for like next generations of their users. So I think that's what's going to happen. What exactly are we going to benefit from? I don't know. I don't think anyone knows, like within 3 to 5 years. But definitely, it probably has to do something with decentralized, specifically due to just like physical reasons, because it's hard to put a lot of compute on the same, like in a very dense way, without suffering too much from like overheating and so on.
Yeah, I mean, I was actually going to say something very similar line. Like I think 2 years ago, when the same discussion happens, lots of people would probably guess, okay, capabilities are increasing. Probably we will have smaller model with much more higher capability. I mean, in a sense, it happened, but at the same time, we are training much bigger models at the same time, right? I think this will just go in the same way, because we want higher capability, probably require, I mean, of course, algorithmic inventions will allow us to do more with less, but still, with the compute, we will probably continue training larger models, but smaller models will also increase, or like capabilities with smaller models will also increase. Like, at least in my view, this is already happening, and this will continue happening, I guess, because now, like if you look at Llama 4, there's very small active parameters with the high capability, but also in total number of parameters is very high, right?